All right, let me get this up here. That's not what I want. I want that Word file. All right, guys, I need you to listen. Okay, I thought what I'd do is just I'm going to read to you this, or look at it. This is their description of what you need to be able to do, okay, in terms of integration. Oh, don't forget Sunday, right, 2 to 6, practice safety test, all right? When you're done, you'll be able to score it yourself and figure out what your score would have been if you had sat down Sunday and taken it. You'll be able to look at what you missed and what you need to work on, okay, because you'll be able to see the objectives that you missed.
Wait, is it what day is it again?
Sunday. This Sunday.
No, not the practice, like the actual.
The date's May 15th.
May 15th.
So we got about a month.
Okay.
Okay? So we still got a month. We got lots of time, but I want to do the practice now so you guys know what you need to work on.
Mm-hmm.
Yep.
You have an idea of how you would do. Just sat down and took it. Okay. All right. So what you should be able to do, integral calculus, you should be able to do a Riemann sum, right? We've done those. Find the area under curve using left, right, midpoint evaluations, and trapezoids. Right? We've done all that, usually with a table. You should know the fundamental theorem of calculus. You know what the fundamental theorem of calculus is? There's two parts to it. That's the
definitions.
The derivative of the integral from 0 to, we'll say f of x here, right, of g of t. dt, remember what to do?
Yeah, you just move the fx down where t
G
is.
of mx times
Derivative of x.
f prime, right? And if that upper limit is x, it's just g of x, right? They are going to test you on that, okay? The other part of the fundamental theorem of calculus is just that an interval represents a net change. So the interval from a to b of f prime of x
Is the net change?
is f of b minus f of a, right? It's just a net change. It's the change from a to b.
Yeah, I remember that.
Okay?
I remember that, yeah.
There were two parts, all right? They'll test you on both. Applications of integrals, you should be able to find the area of a region. The volume of the solid of a known cross-section, that's where we had, squares and triangles and semicircles and all that stuff. The solid of a revolution, so we can spin it around the x-axis, the y-axis, any vertical or horizontal line to find the volume. The average value of a function, you know how to find an average?
Yeah,
How?
find the average.
How do you find the average? What's the formula?
Divide by if it's from like 0 to 6.
1
you do
over
1 over 6.
A
So-
b minus a
Yeah.
There
from
you
the
go.
integral from a to b
Right.
of f
Yeah,
of
we did
whatever
that
it is.
yesterday.
Right, so it's whatever
Yeah.
you want to say the interval from A to B of the function,
There
right?
it is. We did that yesterday.
Yep, well, we're going to keep doing it until we sink it in there.
Yeah.
All right, what else should we be able to do? Okay, you should be able to solve acceleration, velocity, and position problems, right? Either be derivative or motion. Most of your motion is going to be parametric. You should be able to find the length of a curve, including a curve in parametric form. So, do you remember the formula for the length of a parametric curve?
The
Like
integral
the
from
Pi over something.
Oh, no, that's
the
polar.
integral from A to
of
B
square root
of
of
the
the
square root.
derivative squared.
Of the derivative? No.
This is a parametric.
Parametric, I'm parametric first.
Oh. T squared
There you go.
over T squared. plus
dy
T
dt.
dy dt squared, right? Kind of like the Pythagorean theorem is the way that I remember it.
Yeah,
Right?
except it's derivatives.
All right, and then if it's a function, is regular function is square root of 1 plus
dy.
dy dx, or f prime of x, right?
Yeah. Of course.
Squared dx, right? There was a polar form, let's see, do we need polar? It really doesn't say that, right? I don't know. They've stayed away from polar in recent years, so I'm not as worried. I gave the formula. It's like the integral of the square root of, is it r squared plus dr d theta squared? I'm pretty sure. D theta. I'm not sure about that one. I have to look it up. Even I forget these formulas once in a while. Okay.
Yeah.
So that's your
Same.
arc length. You should be able to do that. The area of a region bounded by cold polar curves. You remember the formula for that?
Which one? I'm sorry.
Polar curves. Remember the area of a region bounded by polar curves.
Isn't it like you do circle? No? Okay, never mind. That's my
1/2 r squared d theta.
Oh, well, yeah.
Oh, yeah.
But if you write it like that, I don't know what it is.
Oh, well, we gotta know, yeah.
But
okay.
if you looked at it, like if I looked at it and was like, find the area of this, I could,
All right.
I knew that.
So fundamental theory calculus, we mentioned that once already. Here it is again, right? Derivative and integral, right? What was the fundamental theorem calculus for derivatives?
That,
Is there one?
yeah, there is. I just don't remember
I
what it
can't
is.
remember what it is. We'll go back over that in a few days.
I mean,
All right, techniques of anti-differentiation. This is what I want to focus on. We're gonna start there today. Where is my little bar here? Let me pull my computer. All right, so what should you be able to do in terms of integration? You guys have a little more on you than AB does. They kind of stopped at substitution. You should be able to, here we go, let's read it. Integrate using the power rule and use substitution. So the power rule is the integral of x squared is 1/3 x cubed, and substitution, right? That's an AB topic. You should be able to do integration by parts, right? That's your ultraviolet voodoo. And simple partial fractions. You will never see anything than linear terms. So like, the integral of 1/x squared plus 2x minus 3. You will never see anything more simpler than that where you have to do linear factors and partial fractions, all right? So you're not going to see anything harder than that, all right? You should be able to evaluate improper integrals. You remember what an improper integral is?
Where you
One
can't-
infinity.
Infinity, right? Yeah, you go to infinity or you go around like something that's undefined. Most likely it's going to go to infinity, all right? They won't be real complicated ones, but all right. And rewrite the limits rewrite the limits as a limit as x goes to infinity, right? The way I was taught to do this was just plug in infinity, but AP wants to see you on the free response, right? The limit is as a goes to infinity of the integral from 1 to a or something, okay? They must write that. All right, applications of integrals you should be able to find specific antiderivatives using initial conditions, find the missing constant. You should be able to solve separational differential equations and logistical differential equations. All right, I don't think solve them, but as much as recognize them. They haven't made us solve them yet. You should be able to interpret differential equations via slope fields. Don't be intimidated. The other card in there, just read a slope field. That was pretty easy, right? All right. So today we're going to focus on, so those are some expectations for integration. Today we're going to focus on integration techniques. You should know your integration formulas. That's the first thing I'm going to tell you. I will quiz you sometime this week on all those formulas. All right.
Nice.
Substitution is always your first choice. When you're doing an integral, if it's not as simple like the integral of sine, I'm going to look for substitution. If I can't do substitution, then I'm coming up this flow chart I go through in my head like, can I do integration by parts? Would probably be my next question. Is it improper? Do I need to do a limit? Then I would say, is it rational? Do I need to divide it? Do I need to do partial fractions? I start going through all these options. Is it inverse trig? Right? So these are the things that go through my head. All right. So, for example, if I wanted to evaluate the integral of sine squared, I have seen that pop up once. All right. It's unlikely. To integrate sine squared, you got to use the trig identity. Remember the trig identity for it?
Well, you can break it up with things.
Sine squared is 1 minus cosine squared.
No, 1
That's
minus
That's not
cosine.
going to help us.
2x.
All right.
1/2.
Yeah, it's 1/2. That's the one I want.
I don't know.
That's the same thing as what we said. It's 1 plus or 1 minus cosine.
No, that's not what I want. Cosine 2 theta. This is how I do it. I know this identity because if I know this, I can get the other. Cosine 2 theta is, oh my gosh, I'm forgetting the identity.
1 minus
It's
2
1 minus 2 sine squared.
Yep.
Yep. So if I solve for sine squared, it's going to be cosine 2 theta minus 1 is negative 2 sine squared. So if I divide by negative 2, I get 1/2 times 1 minus cosine 2 theta.
That's what we were
Is
saying.
that what you're telling me? I heard square in
That was
there.
the angle reducing formula.
Yes.
That's
I
what
heard,
I
I'm
was saying.
sorry, I heard square in there, and I was hearing 1 minus cosine squared. Like,
I was
that's not
thinking
She
like,
said square.
Oh, okay, that's what I heard.
sorry, I was
They
thinking,
kind of combined into one thing there, okay?
what,
So that's,
what do you do with the 3 theta though?
well, we have to double, we'll get there. All right, so let's use the identity. So it's 1/2 times 1 minus the cosine of double the angle, so twice 3 theta would be 6 theta, d theta. And this is an integral that you can do, the 1/2 comes out, right? What's the integral of 1? not x. Look at my limits of
Theta.
derivation.
Sorry.
Theta, make sure you make them match. And, the integral of cosine, so, would be sine, right, or negative, because there is sines, negative, cosine, so it'd be plus. Now, let's talk about, I could do substitution, I don't need to, because u would be 6 theta, right?
Why is
So
it
du is 60 theta,
still negative?
Wait,
so I need a
it's
1/6.
It's a minus.
Huh?
minus 1/6.
Derivative of sine is cosine, oh, it's minus, yeah, you guys are. All right, so you need the 1/6
Oh,
out
I
there
haven't
to cover
erased it.
substitution.
Mm-hmm.
And
I
so,
have an eraser.
Oh, maybe I have one like my backpack.
derivative of sine is cosine, because I have that 6 theta, u is gonna be 6 theta, so du, I need to cover the 6, so I put a 1/6 up there, right? You integrate, you divide by the argument, when you differentiate, you multiply by the argument, that's how I do it.
Argument being the
That's
power.
the number in front of theta.
Where'd you get the 6 from? The 1/6?
All right,
Because the
so,
6 theta.
Oh,
let me just go through the substitution. All I know is when I integrate and divide by the argument, when I differentiate or multiply. Because if you let u be 6 theta, right, du would be 60 theta.
But there's no.
So I need a 6 in here,
Oh,
so
so you
I
put the
need
1/6.
I need the 1/6 out front to cover it, right?
makes sense. Cool.
Okay, that's not good. All right. So, unlikely, that would be about as difficult as you would see, I mean, if you see it at all. This one, so my first question is, do you guys substitution? Yeah, right, because the derivative tangent is
Secant squared.
secant squared, so I'm gonna let u be tangent, and x sub du would be
Secant squared.
secant squared. So I have the integral of
Tangent squared du.
u cubed. It's tangent cubed, isn't it?
Oh, yeah.
So it's u cubed, so the integral of u cubed is?
1/3
1/3
u.
u.
No.
1/4.
Okay, 1/4, right?
U to the fourth.
U to the fourth,
Yeah,
but
talking
u is
too
not
fast.
u, u is
Tangent.
tangent, all right? Plus c, right? I'm probably gonna start dropping the plus c's after a while. Okay?
Good, it needs plus C's.
All right.
Losers. All right.
So, I would not preclude something like what you're gonna see, right there, because they've added that to the AB description, so I expect it to be here. What would I do to do this? Oh, we're gonna go lunch.
Division.
Division is the best type
If we
of
don't
division.
put the plus